What is up, everyone? Welcome to this explainer. Look, if you're sitting in high school right now and you're thinking chemistry is just this dry, boring list of rules you got to memorize for your next exam, I need you to hit the reset button on that thought immediately. Seriously. Today, we're completely reframing chemistry. Think of it not as a chore, but as this epic, ongoing quest to understand the very fabric of reality. It's literally the cheat code to the universe, and we're about to unlock it together. So do me a favor real quick. Just take a second and look around the room you're in. Look at the smartphone in your hand. Look at the metal and plastic of your school desk, or even just look at your own hands. Have you ever actually stopped to wonder what invisible building blocks make up all of that? I mean, it's not magic holding it all together, right? There is a hidden architecture to our world. Okay, let's dive right into this. The formal definition tells us that chemistry is the science that studies matter. Its composition, its structure, its properties, and crucially, the transformations it undergoes. But let's be real, what that actually means is that chemistry is our ultimate tool for decoding the universe. It's the language we use to explain how these invisible puzzle pieces of reality connect, break apart, and literally build everything we interact with every single day.
So here's our roadmap for today. First, the magic of matter. Then, history's chemical pioneers. Third, fueling the modern world. And finally, life versus building materials. Starting with Section 1, the magic of matter, where we see how reality transforms. Before we get into the complex stuff, we really have to establish what it is we're actually manipulating when we study chemistry. I think the biggest misconception about matter is that it's just the static, boring stuff sitting there doing absolutely nothing. But in reality, matter is constantly transforming through these incredible exchanges of energy. Chemistry is this wildly exciting, dynamic story. It's about things burning, rusting, exploding, growing. Every single time you cook food, or even when a leaf changes color in the fall, matter is transforming and energy is shifting. That's chemistry in action. Moving into Section 2, history's chemical pioneers, and how we actually started discovering the code.
But how did we actually figure all this out? Because it definitely didn't happen overnight. Looking at the timeline, it's pretty wild. In the ancient era, we had alchemy. People were literally out there trying to use magic and early experiments to turn lead into gold. Kind of chaotic, right? But over centuries, through some absolutely incredible scientific discoveries, it evolved. From the 18th century all the way to the 20th century, brilliant minds transformed our understanding of matter and energy from mystical guesswork into a rigorous, world-changing science.
The very first giant leap happened in the 18th century with this guy, Antoine Lavoisier. He is widely considered the father of modern chemistry. And why? Because he completely rewrote the rules. Before Lavoisier, people had all sorts of wild theories about why things burned or how matter seemingly vanished into thin air. But he stepped up and proved that matter is never lost and never created, it only changes form. His meticulous discoveries laid the foundational bedrock for literally every single modern scientific breakthrough that followed. And this brilliantly illustrates the next massive leap. Over in the 19th century, Dmitri Mendeleev didn't just organize the known elements into a periodic table. It's like he saw the matrix. His organization was so revolutionary, so perfectly attuned to the hidden patterns of reality, that he actually left blank spaces on his table. Think about that. He predicted the existence and even the properties of elements no human being had ever seen yet. And years later, other scientists found them exactly where he said they would be. Absolutely mind-blowing.
Then we get to the 20th century, and Marie Curie enters the scene and absolutely shatters the previous limits of science. Through her relentless and honestly dangerous work, she discovered radioactivity. This was just a heroic breaking of the scientific rules of her time. People used to think atoms were solid, unchangeable little blocks, but Curie proved that certain atoms actually shoot off incredible amounts of energy as they break down. She changed our understanding of energy and matter forever, and she earned 2 Nobel Prizes while doing it.
All right, on to Section 3, fueling the modern world, looking at modern chemistry today.
So you might be wondering, how do we get from 19th century laboratories to solving our daily problems right now? Well, modern chemistry is just way too massive to study all at once, so we break it down. Here's a really quick high-level overview of the modern chemist's toolkit. We basically have 5 main branches: organic, inorganic, physical, analytical, and biochemistry. You can kind of think of these as 5 different lenses you can put on your glasses to look at the exact same universe, but each lens reveals a completely different set of secrets.
Let's zoom in specifically on organic chemistry. This branch is completely obsessed with one very special element, and that is carbon.
Why carbon? Because carbon is the ultimate team player. It bonds with everything. Studying carbon is actually the direct path to refining the fuels that power the cars we drive every single day. But it definitely doesn't stop there. By manipulating carbon chains, organic chemists are also the ones creating the life-saving pharmaceutical medicines you probably have sitting in your bathroom cabinet right now. So from the gasoline in your tank to pain relief, organic chemistry basically runs our daily lives.
And that brings us to section 4, life versus building materials, where we do a little branch comparison. Let's make a real-world comparison here between two vastly different branches of chemistry that you interact with constantly, probably without even realizing it. It's a really sharp, memorable contrast. On one side, you've got biochemistry. This is the chemistry of the inside of living things. It explains your DNA, your proteins, and those super complex medicines your body needs when you get sick. It's squishy, it's biological, and it's infinitely complex. Then, on the other side, we have inorganic chemistry. This branch focuses on metals and minerals. It explains the hard, durable building materials of the outside world, like the massive steel beams and concrete foundations that are literally holding up your school building right now. So it's inside the body versus outside, in the physical world.
Now, what's really interesting about this is how the remaining two branches tie it all together. Physical chemistry is kind of this cool crossover between physics and chemistry. It focuses on thermodynamics, which is heat and energy, and how molecules actually physically move around. Meanwhile, analytical chemistry is straight-up detective work. It uses insane techniques like spectroscopy, which analyzes how light interacts with matter to decode exactly what a material is made of. So together, they measure the movement and decode the light of everything around us.
So from alchemists literally trying to make gold out of lead, to Lavoisier defining matter itself, to the fuels in our cars and the medicines keeping us healthy, chemistry really is an epic story. But here is the most absolutely crucial part. The story is still being written right now. The periodic table, it might have more elements waiting to be found. There are definitely better, cleaner fuels to be invented, and life-saving medicines that haven't even been dreamed up yet. Which leaves me with one final question for you. What future elements, fuels, or medicines will you discover? Thank you so much for joining me on this explainer. Stay curious, and I will catch you next time.